What's going on, everybody? This is Mr. Diamond, and we're going to be doing the example problems for double replacement reactions. Now, how would you be able to tell that these are double replacement reactions? Well, these are going to be some of the easiest to identify because you're going to have two compounds. Notice this is made out of more than one piece, this is made out of more than one piece, and neither of them are water, and the other piece is not a metal oxide or a non-metal oxide. Remember, for synthesis, if we have water plus a metal oxide and a non-metal oxide, you would be having a synthesis reaction. But in this case, we don't have that setup. That means that we have a double replacement reaction. So what do we do for a double replacement? Well, in a double replacement, we are going to replace both pieces. It's as simple as that. Now, the only thing that we're going to have to make sure of is, again, we're going to keep a super heteronormative situation here. We're going to pretend that every one of these elements, the positive pieces, because all of these are going to be ionic, the positive pieces are going to be only dancing with the negative pieces. So you have to make sure that when you go to swap pieces, you want to swap the positive piece and you want to swap the positive piece. You don't want to swap a positive with a negative. You don't want to swap a negative with a positive. So the easiest way to do that is to just get in the habit of switch the first things. Those are what you're going to be swapping. So in this reaction, we have HNO3, which is nitric acid, and CaOH2, which is calcium hydroxide. Notice this is an acid and a hydroxide, so this is actually a neutralization, which is a specific category of double replacement. And we're going to swap our first pieces. So over here, I'm going to use this workspace down here to solve for it. First, I'm going to have my H, and I'm going to have my OH together. We could cross our charges, but just looking at that, you should already be able to figure out, just in case. Well, that is water, so our first piece we're going to get is going to be water, H2O, or you could write HOH, either one is fine. And then we need to figure out our second piece, so that's H is now with the OH, Ca is going to be with the NO3. So we're going to have Ca and we're going to have NO3 together. We need to figure out what charge each of these has, so looking on the periodic table, Ca is in the second column, so that's a 2+ charge. NO3 is a polyatomic, so you have to have that memorized. NO3 would be a 1- charge. We're going to cross our charges. We'll double check. That would be Ca parentheses NO3 2. We can't reduce that. We can't do any sort of tweaks with that, so we're going to put it right here, CaNO3 2. And then we can just pick how we're going to balance it. So remember, water could be HOH. That could help in our balancing situation. We have one H over here. We have one H over here. We have one NO3. We have two NO3s. So to fix that, I'll put a 2 here. That also means that we're going to have two H's and two OH's. So we're going to want to put a 2 in front of our water. We have one Ca, two OH's, two OH's, two H's, two H's, two NO3s, two NO3s. So we are looking good with our balancing. 2, 1, 2, and 1 cannot be reduced. So that is our answer to the question. All right, the next double replacement is a little bit more complicated. We have ZnCl2 plus FeClO3, 3. And the reason this is going to be a little bit more confusing is not because of the identification. Like, it's two compounds, neither of them is water, so we're locked in that we know for sure that this is a double replacement. Apologize, everybody. Recording this on a Friday morning. The problem here comes whenever we swap our first pieces. Okay, we have Zn and Fe that are going to be swapping. Zn we can work with. Zn is going to be with ClO3. Zn is one of them you have to have memorized. Zn is a 2+ charge, and ClO3 is a 1- charge. Again, that's a polyatomic. You've got to know that. We'll cross our charges. We'll get Zn parentheses ClO3 2. Can we reduce that? Nope, we cannot. So we can plug that first piece right into the problem. The next part, though, is where we're going to run into a little bit of weirdness. So our second piece is now going to be Fe with Cl. Again, we don't carry over the subscripts. We're going to have to recross our charges for every single one of these. And this is where the problem comes in. What charge does Fe have? Well, if we check on the periodic table, I've kind of conditioned you that Fe is one of the most common ones that we have this situation with. Fe doesn't have one possible charge, so we normally check back at the problem and we see what Roman numeral it has. but we don't have a problem to check back, or we don't have a word to check back into. So we have to only figure out the charge based on this. So to do that, we are going to have to solve backwards, just like we would have if we were naming it, to figure out what FE's charge is over here, and that's the charge we're going to give FE on this side. So to do that, ClO3 had a -1 charge, so we know this was a 1 minus, and there are 3 of them. That means there is a total of a -3 charge here, and we know it must be electrically neutral, so what charge must Fe have had to cancel out a -3 worth of charges? It would have had to have a +3 worth of charges. And then Cl, we already know from the periodic table, is a 1 minus. We're going to cross our charges. We get FeCl3. That can't be reduced, so let's put that into our formula. Now, this is one of the problems where grouping our ClO3 together is going to be really convenient. We have Cl's here, Cl's here, Cl's here, Cl's here. There's a Cl in every single one of them. But let's separate them and think of these as Cl's by themselves and these as ClO3s, as chlorates, and that's going to help with our balancing. So we have 2 Cl's by themselves here. We have 3 Cl's by themselves over here. So we'll put a 3 there and we'll put a 2 there. We now have 3 ZNs and we have 2 FEs, and if we check, that actually fixes our ClO3s. 2 times 3 is 6 ClO3s, 3 times 2 is 6 ClO3s, 3 ZN, 3 ZN, 2 Fe, 2 Fe, and we are balanced. All right, the last example is obviously harder because it's got words that we're going to have to translate. However, it's not actually going to be much harder than you may think. The difficulty doesn't really increase that much because you already have to be able to figure out the charges on the right sides. Like, we were given the formulas, but we still had to figure out the charges of everything and then cross our charges. So really all we're doing is we're just going to figure them out earlier, and then we get to reuse them on the right side. So we're going to start with aluminum sulfate. Again, we know that these have to be ionic because double replacements will always have ionic compounds. But if we weren't sure, aluminum is a metal, calcium is a metal, so they both start with a metal. So we're going to have aluminum sulfate. This is not my formula. This is going to be me working out the work. Al is a 3+ charge. We know that because it has to be. Sulfate has an 8 ending because it's a polyatomic. Hopefully you know it is SO4, and it's got a 2- charge. We're going to cross our charges. We will get Al2 parentheses SO4 3. And that is the first piece. We are going to be good to plug that into it. But since I didn't leave enough space up here, I'm going to have to write mine down at the bottom. So sorry, I'm being inconsistent there. Al2 SO4 3. Okay, and calcium hydroxide. Calcium is Ca. Hydroxide is another polyatomic. That is OH. Calcium has a 2+ charge. OH has a 1- charge. Find that from the periodic table. That's a polyatomic, so you got to know that. We're going to cross our charges. That's going to give us CaOH. Make sure your OH is in parentheses 2. Cannot be reduced, same as that one. So we're going to do Ca parentheses OH2. And then we're going to put our arrow. But now we know what our positive pieces are and to swap them, but we also know all of the charges. So we're literally just going to flip the pieces but use all the same information we solved for over here. So now Ca, which was a 2+, is going to be with SO4, which was a 2-. And now Al, which was a 3+, is going to be with OH, which was a 1-. We didn't have to re-look up anything. We already figured it out on the other side. So cross our charges, we'll get Ca2SO4 2, which can be reduced. We can get rid of the 2's. And then AlOH3, which cannot be reduced. So we'll have CaSO4. You could put the SO4 in parentheses, but it doesn't need to be because it doesn't have a number with it, plus Al parentheses OH3. And now we balance. Again, it's easier if you keep track of the SO4s and the OHs as a unit because they're the same on both sides. Otherwise, you're going to have to balance the O's, and it's going to be a little bit more frustrating. We have 2 Als over here, so I'm going to put 2 Als right there. 2 times 3 gives us 6 OHs, so we're going to need to put a 3 there so we can get 6 OHs. That gives us 3 CAs, so we're going to have to put a 3 there to get 3 CAs, and that also gives us 3 SO4s, which we need over here. 2 Als, 2 Als, 3 SO4s, 3 SO4s, 3 CAs, 3 CAs, 6 OHs, 6 OHs. So we can put a 1 there. 1332 cannot be reduced. So we are balanced and we are good. All right, that is it for this example video. If you've got any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.